You've seen a speedboat skip across a lake. Fast, loud, bouncing off the surface like a stone. That makes sense. But have you ever watched a 40-ton passenger ferry rise completely out of the ocean and stay there? Not skimming, not bouncing, suspended. Two submerged wings buried 6 feet underwater, holding the entire boat clear of the surface at 45 miles per hour. No hull contact, no spray. Just flight, inches above the waterline. How is that even possible? Why don't we see these everywhere? And if they actually worked, where did they all go? For about 30 years, the engineers who built hydrofoils were absolutely convinced they had cracked the future of water travel. Fast, efficient, elegant. They were right about the physics. They were wrong about almost everything else. And the reason they disappeared has nothing to do with the engineering failing. It has everything to do with what the ocean does to a good idea. To understand why the hydrofoil mattered, you first have to understand what every boat on Earth is actually fighting the moment it starts moving. A conventional ferry hull sits in the water. All of it. The entire bottom surface is in constant contact with the ocean, and every single inch of that contact creates drag. The boat is not gliding through the water. It is bulldozing it, shoving aside a continuous wall of resistance with every foot it travels. And that resistance is the fundamental reason why most ferries top out somewhere around 20 miles per hour, no matter how powerful the engines are. You can double the horsepower and barely gain a few knots, because the problem was never power. The problem was contact. Here is the simplest way to feel this for yourself. Take a dinner plate and drag it through a full bathtub. You can feel the water piling up in front of it, pulling back against your hand. It takes real effort just to move it a few inches. Now lift that plate so only the very bottom rim is touching the surface and drag it again. The resistance nearly vanishes. The plate moves easily because you have taken almost the entire surface out of contact with the water. That is exactly what a hydrofoil does. Except the plate is a 40-ton passenger ferry, and the rim is a pair of precision-engineered underwater wings, generating enough lift to raise the entire machine clear of the surface at speed. The concept is absurdly simple. Get the boat out of the water while it is still on the water. Reduce the contact area from hundreds of square feet to almost nothing. Let physics do the rest. Simple concept. But what happens when those wings actually start working is where it stops feeling like engineering and starts feeling like something that should not be possible. The wings work on the same principle as an aircraft wing. As water flows over the curved upper surface of the foil faster than it flows beneath the flat lower surface, a pressure difference builds between the two sides. That difference produces lift. Not a little lift. Enormous upward force directed straight through the struts and into the hull above. But here is what makes it strange. Below about 15 miles per hour, the foils do absolutely nothing useful. The boat just sits in the water like any other ferry, heavy and slow, dragging its entire hull through the surface. You would never know the wings were even there. Then the engines push the boat past that threshold, and something changes. The foils begin to bite. The lift builds slowly at first, almost unnoticeably. Then suddenly the hull begins to rise. Inch by inch, the entire bottom of the boat lifts clear of the surface. The churning white water underneath disappears. The thunderous resistance that was holding everything back just vanishes, and the boat accelerates hard. Not because the engines got more powerful. They didn't change at all. The boat got faster because now the only things touching the water are two slender foil assemblies and their support struts. A contact area that went from hundreds of square feet to almost nothing in the span of a few seconds. The drag drops by roughly 70% just like that. On the exact same engine power, the boat is now traveling at 45 miles per hour across open water. That is not a modest improvement over a conventional ferry. That is a completely different category of vehicle. and the numbers behind it were genuinely staggering. The Boeing Jetfoil, which ran passenger routes across the Pacific through the 1970s and the 80s, carried 250 passengers on foil assemblies roughly the size of a large dining room table. 2 submerged wings, each about 15 feet across, lifting the combined weight of a fully loaded city bus completely clear of the ocean at highway speed. The engineering was extraordinary. It looked like the beginning of something that would change water travel permanently. Then, the water started winning. Here is how confident the world was in this technology. The Soviet Union started building hydrofoils in the 1950s with the Rakita class and never looked back. They eventually operated over 400 of them across rivers and lakes stretching from Moscow to Siberia. Not a pilot program, not a trial run. A full national transportation network built on boats that flew above the water. And they were not alone. Italy ran hydrofoil services up and down the Mediterranean coast like bus routes. Hong Kong used Boeing Jetfoils on the crossing between the city and Macau, one of the busiest short-distance water routes in the world. The Canary Islands had them. The Adriatic had them. The English Channel had them. Every major maritime nation looked at the same physics, ran the same math, and reached the same conclusion. Short to medium distance routes with high passenger demand and predictable water conditions. The hydrofoil was the obvious answer. And for a while, the math held up beautifully. Passengers loved it. A crossing that used to take 2 hours on a conventional ferry now took 45 minutes. The ride was smooth in calm water, eerily smooth, more like a train than a boat. Operators could run more crossings per day on the same route, which meant more tickets sold, which meant more revenue per vessel. The entire industry was all in. New routes were opening. Fleets were expanding. Manufacturers were scaling up production. The hydrofoil was not being treated as an experiment anymore. It was being treated as the inevitable future of fast passenger water travel. The kind of technology that makes everything before it look primitive by comparison. That was the peak. That was the moment where everyone involved believed the trajectory only pointed upward. Then the real world showed up. And the real world brought problems that no amount of brilliant engineering could outrun. Here is the part that nobody wanted to say out loud during the golden era. The ocean is not a clean environment. A hydrofoil assembly sits 6 feet underwater, moving at 45 miles per hour. That means it is hitting whatever the water contains at the equivalent of a highway impact. Floating debris, submerged logs, crab pot lines, tangled plastic, kelp beds in shallow coastal routes. A piece of driftwood that a conventional ferry hull would barely register becomes a structural event for a hydrofoil. The foil strikes it at speed. The force transmits directly through the support struts and into the hull above. In serious cases, a single debris strike can bend a foil assembly badly enough to pull the entire boat out of service for days. One log, one crossing. Days of lost revenue. But debris was actually the problem you could see coming. Here is the one you couldn't. Biological fouling. The slow, invisible accumulation of barnacles, algae, and marine growth on any surface that sits underwater long enough. On a conventional hull, it is an annoyance. On a hydrofoil wing, it is a performance killer. A fouled foil surface disrupts the smooth water flow that generates lift. The boat needs more speed to get airborne. It burns more fuel getting there, and eventually it stops rising cleanly at all. Fixing this means hauling the entire vessel out of the water on a schedule that conventional ferries never require. Expensive, time-consuming, and completely unavoidable. Then there is the wave problem, and this one is genuinely counterintuitive. Rough water does not just make a hydrofoil uncomfortable, it makes it operationally dangerous. When the hull is up on foils in a beam sea, a large wave does not lift the whole boat evenly the way it would a conventional hull. It hits the foils at different angles. The foil on the windward side rises out of the water and loses lift. The foil on the leeward side bites deeper and generates more. The boat rolls hard and fast, faster than passengers can brace for, faster than instinct can compensate. Hydrofoil routes were being canceled for weather at rates that shocked even the operators who had studied conditions carefully before committing to service. The technology that made calm water feel like riding a train made rough water feel like a crisis. And underneath all of this sat one uncomfortable truth. A conventional ferry hull is a simple, rugged shape. A hydrofoil is a precision instrument with tolerances measured in fractions of an inch and hydraulic systems that are deeply unhappy about salt water. The ocean does not care about precision. Now here is where the problems stop being physical and start being financial. A hydrofoil running at 45 miles per hour burns fuel at a rate that would make a conventional ferry accountant physically uncomfortable. The engines are not just working hard to maintain speed, they are working hard to maintain altitude. Every second the boat is foil-borne, the system requires continuous power just to keep the hull above the surface. But here is the part that really breaks the economics. Drop below the threshold speed and the hull falls back into the water. The drag slams back in instantly, and you are suddenly a very expensive conventional ferry going nowhere fast. That means a hydrofoil cannot throttle back to save fuel on a quiet Tuesday, the way a normal vessel can. It is either flying or it is wallowing. There is no economical middle setting. On a route with high predictable passenger loads, that constraint is manageable. You fill the seats, you run the crossing, the revenue covers the burn. But on a route where demand fluctuates by season or day of the week, running a hydrofoil at half capacity with full fuel cost is a financial catastrophe in slow motion. Operators learned this the hard way across dozens of routes through the 1970s and 1980s. And the lesson arrived at exactly the worst possible moment. Because in the 1980s, the high-speed catamaran showed up. Two narrow hulls, a wide stable deck between them, lightweight aluminum construction and water jet propulsion. No foils, no hydraulics, no debris vulnerability. Top speed in the range of 35 to 40 miles per hour on most routes. Not quite as fast as a hydrofoil. Close enough that most passengers did not care about the difference. The catamaran did not beat the hydrofoil in a straight speed comparison. It won on every other line in the spreadsheet. Fuel cost per passenger mile, maintenance hours per crossing, weather cancellation rate, useful service life before major overhaul, route flexibility in shallow or debris-heavy water. One by one, operators across the world ran the numbers and reached the same conclusion. The faster machine was also more expensive, more fragile, more restricted, and more dependent on perfect conditions. By the late 1990s, most commercial hydrofoil services had been retired or replaced. But the hydrofoil did not actually disappear. It did what every over-engineered technology does when the commercial math stops working. It retreated to the environments where its particular combination of speed and capability has no cheaper substitute. The United States Navy runs hydrofoil-derived foil systems on small patrol and interdiction vessels, where 45 miles per hour in coastal water is not a commercial nicety. It is a tactical requirement. Speed at that level is worth the maintenance cost when the mission demands it. In competitive sailing, the America's Cup yachts now fly on hydrofoil systems that put the entire boat airborne at speeds above 50 miles per hour. The wing sails are managing aerodynamic forces. At the same time, the foils are managing hydrodynamic ones. They are simultaneously sailing and flying. The physics never changed, not even a little. The lift is the same. The drag reduction is the same. The engineering is the same. What changed is the context around it. The engineers of the 1960s were not wrong about what the hydrofoil could do. They were absolutely right about that. They were wrong about how many routes would remain profitable once the real-world cost of doing it became clear after a decade of actual operation. The technology was never the problem. The spreadsheet was. So here is where you land. You saw a boat rise out of the water on two underwater wings and thought you were watching the future arrive. And you were. The future just turned out to be more expensive, more fragile, and more weather-dependent than anyone wanted to admit. Speed in isolation is not a product. Speed combined with reliability, reasonable maintenance, and the ability to run in bad weather is a product. The hydrofoil delivered one of those things brilliantly and struggled with every single one of the others. It did not lose to a dramatic failure or a fatal flaw. It lost to the slow, relentless arithmetic of operating costs, weather logs, and maintenance schedules repeated across hundreds of routes until the spreadsheets all told the same story. And if you think that story ends with the catamaran that replaced it, it doesn't. Because those two narrow hulls moving fast through water have a physics problem of their own.